Welcome to the deep dive. Today, we're jumping into your sources that describe a really fundamental shift in how we think about solving complex problems, especially when it comes to training deep neural networks.
It's this idea of moving away from just optimizing to something more like creation. For decades, the goal was always to find that one single best answer, the highest peak on the mountain.
But that approach is incredibly brittle.
It is. Because as systems get more complex, if the environment changes even a tiny bit, that single perfect solution can just completely fail.
And that's where this concept of quality diversity, or QD, comes into the picture. It's a totally different goal.
Exactly. With QD, the mission isn't to find one champion. It's to generate a huge, diverse collection of high-performing solutions. We call it a repertoire.
A repertoire, so like a library of good answers.
Think of it like natural evolution. It doesn't produce one perfect animal. It produces a whole ecosystem of animals, each one adapted to a different niche. That's the kind of robustness we're after.
And the main algorithm driving this whole field is called map-elites, or ME for short. How does it actually manage to find things that are both high quality and diverse at the same time?
Well, it's actually pretty elegant. You start by defining what you care about in the solution's behavior. We call this the behavior descriptor space.
So for a robot, that might be its speed and, say, how it walks.
Yeah, exactly. Speed and foot contact pattern. Then you take that space and you chop it up into a grid like a chessboard. The algorithm's only job is to find the single best performing solution for every single cell in that grid.
And if a new solution lands in a cell that's already filled, but it's better,
You replace the old one. So you're always pushing for higher quality within each unique behavioral niche.
and this isn't just a theory, right? This has had some pretty big real-world successes.
Oh, absolutely. The classic example that really put ME on the map was with hexapod robots, the six-legged ones.
Okay.
Because ME generated hundreds of different ways for the robot to walk. Some fast, some slow, some favoring certain legs. The robot could adapt instantly if it got damaged.
So if a leg breaks off,
It doesn't have to stop and relearn. It just dips into its repertoire, finds a high-performing five-legged gait, and keeps on going. It's true resilience.
okay, so here's where the plot thickens. The original map-elites used basically random search, just evolutionary guesswork.
Right, it's like throwing darts at a board. And while that's simple, it becomes incredibly sample-inefficient when you're dealing with really high-dimensional problems.
Like training a deep neural network.
Exactly. You're asking evolution to tweak millions of parameters with no guidance. It's just too slow. So researchers realized they needed to borrow the machinery of deep reinforcement learning, or RL, to get that gradient information.
And that's the central tension for our deep dive today. This attempt to mix the efficiency of gradient-based RL with the stability of evolutionary search.
And our mission is to unpack this new framework, PBT Map-elites, which seems to have finally cracked the code on how to combine these two worlds without everything falling apart.
We should probably define PBT right away.
Good call. PBT is population-based training. It's a method where you train a whole population of models at the same time, and they can learn from each other and even change their own training rules as they go.
Okay, so let's dig into why this blend was so necessary, but also why the first attempts were so problematic.
Well, the need was clear. As soon as people started using these huge, deep neural networks for policies, the old methods like pure evolution strategies or black box optimization just couldn't keep up.
Because they're gradient-free. They just look at the final score, not how to get there.
Precisely. To handle the sheer scale of deep networks, you really need to use gradients to guide the search efficiently. It's what standard RL is built on.
So these early hybrid methods, things with names like QDPG and PGA map-elites, they started adapting RL algorithms like TD3. And they did get some good results, right?
They did. They achieved state-of-the-art on some tough robotics problems, especially ones with sparse rewards where you need a ton of exploration.
And it's a big but.
A very big but. This blend introduced four major crippling downsides that kind of undermine the whole point of using map-elites in the first place.
Let's walk through them because they really set the stage for why PBT map-elites was such a necessary invention. First up, hyperparameter sensitivity.
This is the classic RL headache, but magnified. RL algorithms are, notoriously finicky. They need you to tune things like learning rates and exploration noise just right for your specific problem.
Get it wrong and the whole thing just collapses.
It just diverges. And this was a burden that pure evolutionary methods never had. By bolting on RL, they put this huge, fragile tuning task right back on the user.
Which leads to the second problem, Instability.
Yeah, you're injecting all this randomness from gradient descent into a big population, and the whole training process just became incredibly stochastic and unstable. You'd run the same experiment twice and get wildly different results. It's just not reliable.
The third issue sounds more like an engineering problem, but a really frustrating one. Inflexible design.
It was. These early methods were hard-coded to a specific RL algorithm, usually TD3. If TD3 just wasn't a good fit for your environment, which happens a lot,
The whole framework was useless.
the whole thing fell apart. It had no generality.
And the fourth problem feels like it goes against the very spirit of evolution. The scaling issues from shared components. Why was sharing things like a replay buffer such a bad idea?
It just completely breaks the parallel nature of evolution. In a traditional evolutionary algorithm, every individual is independent. You can run them on thousands of different computers without any issue.
But if they all have to talk to one central replay buffer,
You create a massive bottleneck. And even worse, you get this problem where poor performing agents can actually poison the well. They fill up the shared buffer with bad data, which then drags down the training of your high-performing agents.
so the very thing they added for efficiency actually killed scalability and robustness. They fixed one problem and created four more.
Pretty much. They needed a complete rethink, a way to get the power of gradients without all that baggage.
And that takes us to the solution. PBT map elites. The big innovation here wasn't just a tweak to the algorithm, it was a change in what they were evolving. They moved from evolving just a policy to evolving a population of full agents.
That's the key. And when we say full agent, we mean the whole package. It's a tuple that includes, of course, the policies, parameters, theta.
The brain of the agent.
Right. But it also includes all the other learnable stuff, like the critic networks you use in RL. And this is the most important part. It also includes the hyperparameters, the learning rates, the exploration noise, all of it.
So evolution gets to control the learning process itself. It's not just learning the task, it's learning how to learn the task.
Exactly. And the PBT framework manages this through two interconnected updates. The first is the population update, which is all about quality.
How does that work?
You've got this large population of agents, each training independently with its own settings and its own data. Periodically, you stop and rank them by fitness. The worst 20% are just thrown out and replaced by copies of the top 10%.
Standard elitism, survival of the fittest.
It is, but here's the clever twist to bring diversity back in. On top of that, they also replace a big chunk of the middle of the pack agents, about 40%.
But not with copies of the best ones.
No, they're replaced by agents sampled randomly from the map elites repertoire.
Ah, that's brilliant. So you're constantly re-injecting diverse, high-performing solutions from your library back into the training population.
It forces the system to keep exploring. It prevents the whole population from just converging on one single solution, even though they're all using efficient gradient-based methods.
And this is also where the meta-learning happens, right? With the hyperparameters.
Yes. Whenever an agent gets replaced, whether by an elite or one from the repertoire, the new copy gets a fresh set of hyperparameters, randomly sampled from a predefined range.
So the system is constantly experimenting. What if I tried a higher learning rate over here? Or more exploration noise for this type of behavior?
That's it. Hyperparameter tuning is no longer this thing a human does beforehand. It's baked into the evolutionary process itself.
And this design elegantly solves those four big problems we talked about. Because every agent is independent, its own parameters, its own critic, its own replay buffer, the whole system is trivial to parallelize.
The scaling problem is gone.
And the inflexibility problem is gone too. You can just slot in whatever RL algorithm you want, SAC, TD3, whatever. The PBT wrapper handles the rest.
Exactly. And after that PBT phase, you get the second update, the repertoire update, which is purely focused on filling out that library of diverse solutions.
So you take your trained agents, evaluate them, and place them in the grid.
Right. But they also added another evolutionary operator here to keep pushing the boundaries called the ICLR variation operator.
And what's that doing?
It's a smart way to create novel offspring. It takes two good policies from different parts of the repertoire and sort of interpolates between them in the behavior space. It's designed to generate a new policy that is very likely to land in a completely empty cell in your grid. It's all about maximizing coverage.
Okay, so the framework seems really solid. PBT manages the quality and tuning, and the repertoire update pushes for maximum diversity. Let's get to the results. They tested this on a bunch of robotics tasks.
5 environments, all in the BRX simulator, which is super fast. They had what they called uni environments, walker, ant, half cheetah, where the goal is basically just to run fast in different ways.
And then the really hard ones, the trap environments.
The trap environments.
Yeah.
Anti-trap and the big one, humanoid trap. These are notoriously difficult because to get a high score, the robot has to first perform a tricky maneuver, like sidestepping a pit, that has a really deceptive low initial reward.
You need a ton of exploration to find that one safe path.
You do. And looking at the overall results, PBT map elites, particularly the version using the SEC algorithm, was either on par with or just flat out better than all the previous state-of-the-art methods.
But the real story is in the humanoid trap, isn't it? That one was kind of the final boss for these algorithms.
It was. This environment had been basically unsolvable for most map elites methods before this. And PBT map elites with Seka was the only method that was able to solve it within the training budget.
The only one. What about the others?
The older TD3-based methods were so unstable they often couldn't even get the humanoid to run properly, let alone navigate a complex trap. It was a complete breakthrough.
So the stability of SAC combined with the smart tuning of PBT was the secret sauce?
That's what it looks like. And the comparison they did with standard PBT was also really telling.
Standard PBT just optimizes for the single best score. It doesn't care about diversity.
Right. And on the simple environments, standard PBT actually got a slightly higher top score, which makes sense. It's not wasting any effort filling a repertoire.
But on the trap environments,
The story completely flipped. That pressure to be diverse, to fill the repertoire, was absolutely essential for discovering the complex exploratory behaviors needed to get past the trap. PBT map elites found the optimal path, while standard PBT just got stuck.
and this all comes back to that dynamic hyperparameter tuning. It wasn't just a fluke. You could actually see it happening.
You could. The visualizations are amazing. You can see these maps of hyperparameters that the algorithm learned on its own. On the ANT trap, for example, agents that were in the behavior region corresponding to stuck near the trap.
The ones that needed to explore more.
The algorithm dynamically gave them higher exploration noise.
Yeah.
It cranked up the randomness to help them break free.
And then as soon as an agent figured out the sidestep and started getting high rewards,
The algorithm immediately turned the exploration noise back down, letting the agent exploit that new high-reward path and just focus on maximizing its speed. It's this incredible dynamic adaptation that you just can't get with fixed hyperparameters.
So if we pull back, the big conclusion here is that changing the problem from evolve a policy to evolve a full agent policy parameters and hyperparameters was the key.
It gives you this incredible combination of flexibility, scalability, and performance. You get the sample efficiency of gradient-based RL, but with the stability and broad search power of evolution.
So for you listening to this, trying to build or research these kinds of systems, what's the takeaway? This approach basically automates away one of the biggest pains in RL manual hyperparameter tuning. And that automation led directly to better performance, especially on the hardest exploration problems out there.
It's a huge step. They solved the humanoid trap with under 150 million simulator steps. For context, previous methods would have needed tens of billions of steps to even get close. So it leaves you with this really provocative question.
Go on.
If letting evolution take control of these internal non-policy parts of an agent, things like learning rates and noise levels, is this powerful? What else should we be letting it control? Should the very architecture of the neural network itself also be part of the evolutionary process? It's something for you to think about.